Hi students, today we're talking about derivative applications. Specifically, we're going to talk about the first and second derivative rules. This is using what we know about derivatives to make some sense of graphs. Alright, first off we got to sketch a graph that has two local maxes, an absolute max and an absolute minimum. One way to deal with this would be to think about this, okay, there's my absolute minimum. Local max, absolute max, and kind of stopping this in this way. Local max can also be an absolute max, so technically there are three local maxes here, and there are 1, 2, 3 local minimums as well. The endpoints are also local max and min values, but we're not really concerned about that right now. The big idea is that we've got an absolute max and absolute min and some various local extrema. All right, we've got this beautiful graph of f of x. I'm going to identify some extreme values. I've got a local minimum, I've got a local maximum, I've got a local minimum, and that's it. The value of the derivative at that point, so we've got a negative slope turning into a positive slope. I'm going to say f prime goes from negative to positive because we can see our graph goes from decreasing to increasing. Therefore, f prime, the slope, goes from negative to positive. All right, around my other, keeps accidentally switching to eraser. At my other local minimum, f prime also goes from negative to positive because we're going from decreasing to increasing. All right, for the other part, we're going for our maximum, and here my graph's going from increasing to decreasing, and that means that f prime changes from positive to negative. All right, so it seems like we have some patterns here. This leads us to something called the first derivative test. The first derivative test basically says that when f prime of x changes sign, we're going to have a caveat, a warning in here in a second. I'm going to put from positive to negative. F of x has a max. In other words, we're going from increasing to decreasing in our graph, positive slope to negative slope in our graph. If we're looking from negative to positive, then f of x has a local minimum. In other words, we're going from negative slope to positive slope. We're going from decreasing to increasing. The warning I'm going to put here is that f must be continuous for this to work. We could have a graph that looks something like this. And we certainly have a positive derivative before, a negative derivative after. This is not necessarily going to let us work with what we are comfortable with local max and min values. So we're dealing with this in terms of only continuous functions. All right, using this, we've got x cubed minus 16x. We're going to see this on the next page. I'm going to find f prime of x, which shouldn't be too scary for us, which can be 3x squared minus 16. Cool. And the first derivative test to find any extrema means that we've got to figure out where this thing is equal to 0, because that's when we change sign. So when we do that, we end up getting x is equal to plus or minus 4 over the square root of 3. Mr. Carlson, where are you coming up with these awful numbers from? Whatever, we'll deal with it. Okay. One way for us to think about this is that at each of these places, so 4 over the square root of 3 on the negative side, 4 over the square root of 3 on the positive side, we have some kind of behavior going on here. And if this is a parabola with a positive a value, so it's going to look something like this, the graph of the derivative, our graph is going to look something like this. What that means is that at negative 4 over the square root of 3, f prime changes from positive to negative. And here we're going from f prime goes from negative to positive. That means something about the extreme values of this graph. That we're going to have a max at negative 4 over square root of 3, and we're going to have a min at 4 over the square root of 3 based on our derivative rules. We also have this idea that if we have a max here, our graph might look something like this. And I made an assumption which is not healthy, which is that that will actually go through that point. I don't want to make that assumption. I'm going to do this in yellow so I can actually do this. So we've got a max value here, and then a min value here. And if I think about this in terms of what I know about cubic graphs, x cubed minus 16x, this looks kind of cubic to me. This looks like something that I could make sense of based on what I know about polynomials. Oh, and look, here's that same graph. I love it. And this is kind of what we predicted. There's that really gross number, 2.309. We knew that that's what that was. And now we're going to consider the second derivative of this graph. So this is a graph of our function. Second derivative describes something called concavity. And I'm just going to talk about that here. Things that are concave up are when the second derivative is greater than 0, and things that are concave down are when the second derivative is less than 0. And just to be really clear, that doesn't have to be like a whole cup there. This could be decreasing and concave down, or it could be decreasing and concave up, or increasing and concave up. It could be increasing and concave down, and decreasing and concave down. So I'm going to identify some places on here. Here it looks all like we're concave down, and that continues curving down up until right here. And then we're concave up, we're concave up, we're concave up, all the way up until the end. This suggests that f double prime is less than 0 here, f double prime is greater than 0 here. Okay, that's graphically, and I think I meant to do this in opposite order. We said that the first derivative of this was 3x squared minus 16. The second derivative, f double prime of x, is going to be 6x. Oh, and that 16 goes away. That's going to be 0 when x is 0. And one of the things that happens here is that we have a point of inflection. We're changing from a negative second derivative to a positive second derivative. That changes this concavity. The other thing that I'd like you to notice is that if we knew the derivative was equal to 0 here and here, which we do, if we're concave down, there's no other way for this to be but a maximum. So if we're continuous, that's this big thing. If we're differentiable is more important, actually, because that takes that into account. And we have f prime is equal to 0. F double prime is less than 0. That means we have a maximum at that place. This is called the second derivative test. So same thing here. f prime equals 0, f double prime is greater than 0, in other words, we're concave up. That has to be a minimum. There's no way to make a horizontal tangent line and be concave up unless that's a local minimum. All right. Here we've got a graph of random functions that give us f prime and f double prime. One of those, I think, is the one we were just playing with. We're looking to find the value of, I'm going to make these a little bit clearer, f double prime at mins and maxes, and also f prime at mins and maxes. So let's talk about f first. So at a min and a max, I'm going to call this the max, is at negative 2.309. And a min is going to be at 2.309. F prime at each of those places, that's where we're crossing the x-axis. That's going to be 0, which makes sense because we have horizontal tangent lines. F double prime, that is my green graph. I'm going to make that green just so we can talk about that easier. Here we are negative, and here we are positive. This is a visualization of what we talked about in the previous slide, that if f prime is 0 and f double prime is negative, we have a max. And if f prime is 0 and f double prime is positive, we have a min. Let's see if that holds true here as well. And I want to say it's my red graph that's labeled. Yes, my red graph is the one we care about. So we've got a max here. And that's going to be at negative 2.029. I can see another one here, but it's probably at positive 2.029, but I don't really care about that right now. And we've got a min at 0. I don't care about that right now because I can't see what number that is, so I'm just going to skip it for a minute. Okay, I'm guessing my blue graph is going to be my derivative just to keep these things consistent. And I notice at that point for the max, we've got a value of 0. It's also going positive to negative. Same thing for at 0. We've got a value of 0. We're going from negative to positive here. For my second derivative, we are less than 0 for my max. And for my second derivative, we are greater than 0 for my minimum. That jives with everything we've been talking about so far. All right, just to kind of summarize, f double prime describes concavity. So if it's greater than 0, it's concave up. And that's f. F double prime is less than 0, means that f is concave down. Concavity changes, so in other words, when f double prime changes sign. And we call this a point of inflection. And then the last question on this page, what does the second derivative test tell you? It tells you based on the first and second derivative. So when f prime of x is equal to 0, it's a terrible x, but that's fine. And f double prime is greater than 0, we have a minimum. When f double prime is less than 0, in other words, we're concave down, we have a maximum. To figure out where extrema are, without graphing it, we've got to do a couple things. We've got to take the derivative. This is going to let us find some critical values. Critical values happen when well, that's fun. Values when f prime of x is equal to 0 or f prime of x is undefined. These are things that we have to then check to see if they are positive or negative in terms of first or second derivatives. We've got two options. One is the first derivative test. And if f prime is going from positive to negative, we're talking about a max. If f prime is going from negative to positive, we're talking about a minimum. The other option we have is the second derivative test. That starts from the same beginning point where f prime is equal to 0. If f double prime is less than 0, our graph is concave down. It's a maximum. And if f double prime is greater than 0, our graph is concave up. It's a minimum. We also need to be able to be very careful with some of these words. We know that increasing, decreasing, constant have to do with the shape of a graph. Concave up and concave down have to do with the curvature of the graph. But something can be both increasing and concave down or decreasing and concave up. We also have to begin to be comfortable with making sure that if we say the word positive, that does not mean positive slope. Positive just means above the x-axis. And negative just means below the x-axis. We know these things, but we have to be a little bit careful about applying them.